Series parallel combination circuits. What is a series parallel circuit? With simple series circuits, all components are connected end-to-end to form only one path for electrons to flow through the circuit. With simple parallel circuits, all components are connected between the same two sets of electrically common points, creating multiple paths for electrons to flow from one end of the battery to the other. With each of these two basic circuit configurations, we have specific sets of rules describing voltage, current, and resistance relationships. Series circuits. Voltage drops add to equal total voltage. All components share the same equal current. Resistances add to equal total resistance. Parallel circuits. All components share the same equal voltage. Branch currents add to equal total current. Resistances diminish to equal total resistance. This circuit is neither simple series nor simple parallel. Rather, it contains elements of both. The current exits the bottom of the battery, splits up to travel through R3 and R4, rejoins. Then splits up again to travel through R1 and R2. Then rejoins again to return to the top of the battery. There exists more than one path for current to travel, not series. Yet there are more than two sets of electrically common points in the circuit, not parallel. Analysis technique. Step 1. Assess which resistors in a circuit are connected together in simple series or simple parallel. Step 2. Redraw the circuit, replacing each of those series or parallel resistor combinations identified in Step 1 with a single, equivalent value resistor. If using a table to manage variables, make a new table column for each resistance equivalent. Step 3. Repeat steps 1 and 2 until the entire circuit is reduced to one equivalent resistor. Step 4. Calculate total current from total voltage and total resistance IR. Step 5. Taking total voltage and total current values, go back to last step in the circuit reduction process and insert those values where applicable. Step 6. From known resistances and total voltage total current values from Step 5. Use Ohm's law to calculate unknown values voltage or current IR. Step 7. Repeat steps 5 and 6 until all values for voltage and current are known. In the original circuit configuration, essentially, you will proceed step by step from the simplified version of the circuit back into its original, complex form, plugging in values of voltage and current where appropriate, until all values of voltage and current are known. Step 8. Calculate power dissipations from known voltage, current, and/or resistance values. In the example circuit above, R1 and R2 are connected in a simple parallel arrangement, as are R3 and R4, having been identified. These sections need to be converted into equivalent single resistors, and the circuit redrawn. The double slash symbols represent parallel to show that the equivalent resistor values were calculated using the 1,1R formula. The 71.429 ohm resistor at the top of the circuit is the equivalent of R1 and R2 in parallel with each other. The 127.27 ohm resistor at the bottom is the equivalent of R3 and R4 in parallel with each other. When we add those two equivalent resistances, we get a resistance of 198.70 ohm. Now we can redraw the circuit as a single equivalent resistance and add the total resistance figure to the rightmost column of our table. The dash symbol is used here to represent series, just as the slash symbol is used to represent parallel. Back to our equivalent circuit drawing. Our total current value of 120.78 milliamps is shown as the only current here. Now we start to work backwards in our progression of circuit redrawings to the original configuration. The next step is to go to the circuit where R1//R2 and R3//R4 are in series. Now we start to work backwards in our progression of circuit redrawings to the original configuration. The next step is to go to the circuit where R1//R2 and R3//R4 are in series. Since R1, R2, and R3, R4 are in series with each other, the current through those two sets of equivalent resistances must be the same. Furthermore, the current through them must be the same as the total current. So we can fill in our table with the appropriate current values, simply copying the current figure from the total column to the R1, R2, and R3, R4 columns. Now, knowing the current through the equivalent resistors R1, R2, and R3, R4, we can apply Ohm's law to the two right vertical columns to find voltage drops across them. Because we know R1, R2, and R3, R4 are parallel resistor equivalent, and we know that voltage drops in parallel circuits are the same, we can transfer the respective voltage drops to the appropriate column on the table for those individual resistors. In other words, we take another step backwards in our drawing sequence to the original configuration and complete the table accordingly. Finally, the original section of the table columns R1 through R4 is complete, with enough values to finish. Applying Ohm's law to the remaining vertical columns, we can determine the current through R1, R2, R3, and R4 individually. Redrawing complex schematics with electric circuits and circuit diagrams. The length and routing of wire connecting components in a circuit matters little. In this case, I'll begin my tracing of this circuit at the negative terminal of the battery and finish at the positive terminal in the same general direction as the electrons would flow. When tracing this direction, I will mark each resistor with the polarity of negative on the entering side and positive on the exiting side, for that is how the actual polarity will be as electrons enter and exit a resistor. Any components encountered along this short loop are drawn vertically in order. In this case, there's a loop around R1 formed by R2, and another loop around R3 formed by R4. It is identical to the 4-resistor series parallel configuration we examined earlier in the chapter. With only one remaining resistor left to trace, then next step is obvious. Trace the loop formed by R2 around R3. Adding R2 to the vertical drawing, and we're finished. The result is a diagram that's very easy to understand compared to the original. Building series parallel resistor circuits. A breadboard appears to be nothing but a plastic frame with hundreds of small holes in it. Underneath each hole, though, is a spring clip which connects to other spring clips beneath other holes. The connection pattern between holes is simple and uniform. Suppose we wanted to construct the following series parallel combination circuit on a breadboard. The recommended way to do so on a breadboard would be to arrange the resistors in approximately the same pattern as seen in the schematic, for ease of relation to the schematic. If 24 volts is required and we only have 6-volt batteries available, 4 may be connected in series to achieve the same effect. This is by no means the only way to connect these 4 resistors together to form the circuit shown in the schematic. Consider this alternative layout. In this method, components and wires are secured by mechanical tension underneath screws or heavy clips attached to small metal bars. The metal bars are mounted on a non-conducting body to keep them electrically isolated from each other. Building a circuit with components secured to a terminal strip isn't as easy as plugging components into a breadboard, principally because the components cannot be physically arranged to resemble the schematic layout. Instead, the builder must understand how to bend the schematic's representation into the real-world layout of the strip. Consider one example of how the same 4-resistor circuit could be built on a terminal strip. Another terminal strip layout, simpler to understand and relate to the schematic, involves anchoring parallel resistors to the same 2 terminal points on the strip like this. Building more complex circuits on a terminal strip involves the same spatial reasoning skills, but of course requires greater care and planning. Take for instance this complex circuit represented in schematic form. The terminal strip used in the prior example barely has enough terminals to mount all 7 resistors required for this circuit. It will be a challenge to determine all the necessary wire connections between resistors, but with patience it can be done. First, begin by installing and labeling all resistors on the strip. The original schematic diagram will be shown next to the terminal strip circuit for reference. Next, begin connecting components together wire by wire as shown in the schematic. Overdraw connecting lines in the schematic to indicate completion in the real circuit. Watch this sequence of illustrations as each individual wire is identified in the schematic, then added to the real circuit. Step 1. Step 2. Step 3. Step 4. Step 5. Step 6. Step 7. Step 8. Step 9. Step 10. And Step 11. An example of a variant wire connection might be the very last wire at Step 11, which I placed between the left terminal of R2 and the left terminal of R3. This last wire completed the parallel connection between R2 and R3 in the circuit. However, I could have placed this wire instead between the left terminal of R2 and the right terminal of R1. Since the right terminal of R1 is already connected to the left terminal of R3, having been placed there in Step 9 and so is electrically common with that one point. Doing this, though, would have resulted in 3 wires secured to the right terminal of R1 instead of 2, which is a Fox-Pax internal strip etiquette. Would the circuit have worked this way? Certainly, it's just that more than 2 wires secured at a single terminal makes for a messy connection, one that is aesthetically unpleasing and may place undue stress on the screw terminal. While this poses no electrical problem, it might cause confusion for anyone measuring resistor voltage drops with a voltmeter, especially an analog voltmeter which will peg down scale when subjected to a voltage of the wrong polarity. For the sake of consistency, it might be wise to arrange all wire connections so that all resistor voltage drop polarities are the same, like this. Though electrons do not care about such consistency and component layout, people do. This illustrates an important aspect of any engineering endeavor, the human factor. Whenever a design may be modified for easier comprehension and/or easier maintenance, with no sacrifice of functional performance, it should be done so.